Welcome to a new tutorial from DIERS International. In this video we will work together through the result pages of a static foot pressure measurement using the DIERS pedoscan system. Now in 2006, DIERS pedoscan was the first hardware extension of the DIERS core product Formetric 4D. For the first time it was possible to perform simultaneous recordings to interpret posture parameters along with a pressure image of the feet. This function enormously expanded the range of clinical application of DIERS products and was also the cornerstone for a functionally oriented approach, which was further developed in the following years to a holistic gated walking analysis. Now, let's dig a bit deeper into the results display of a static foot pressure measurement. The significance of the result pages is divided into three primary focus points. First, the subjective pressure image that the feet project onto the floor, possible as a still image of the average pressure or as a time progression. This can often be used to identify a conspicuous foot position. Second, the quantified load distribution of the stance position between the right and the left foot, as well as the forefoot and the rear foot. Very interesting, especially in comparison with the data of the spinal analysis. Third, quantifying center of pressure variation as an expression of body sway, coordination and autoregulation. The parameter area in the upper part of the first results tab summary displays the pressure distribution in short, clear diagrams. Here on the left you will find the force distribution between the right and the left foot, between the forefoot and the rear foot, and the maximum force value under each respective foot. In diagram 3, all data related to the left side are displayed in red. All right data then is blue. Where possible, green stripes in the graphs mark the normative expected value. An equivalent distribution of 50% to each side is expected for the left and right force distribution, although this should always include a tolerance range of ±5%. This can be used to directly accommodate a relief posture such as may arise in a pain-related or perhaps a post-operative situation. This also applies to the anterior-posterior force distribution, whereby the normative expected value here should be 40 to 60%, forefoot to rear foot. Unfortunately, the value given in this way cannot directly equate it with a sway back or forward-leaning posture type, since in the upward construct various pivot points can provide alignment correction. For example, an increased rear foot load in the pelvis can be converted to a forward tilt of the trunk. This already shows how interesting the combination of spinal and foot pressure measurement is. The maximum force value can have various causes, ranging from actually overloaded foot zones, pressure points or calluses, to pressure maxima caused by bones. A clinical interpretation is therefore difficult. Let's move to the right side of the parameter field. The surface directly reflects the area of the sensors that registered pressure during the measurement. In the sense of a balanced lateral distribution, reasonably equal values should also be expected here. Foot rotation normally lies in a relatively broad range between 10 and 15 degrees of external rotation. More noticeable rotation deviations in the static measurement are often a reflection of an already more advanced dysfunction. In many cases of functional compensation mechanisms, the effects of excessive external rotation or internal rotation are initially only visible in the dynamics and only become apparent in a static impression when they are more pronounced. About the COP rotation parameter. The term COP is an abbreviation for center of pressure. If each foot is considered separately, the pressure signals measured beneath it combine to form a center of pressure. If we now place both center of pressure points in the area of the pressure measurement platform, then balanced statics would expect the line connecting both points to be parallel to the line between the heels. If the COP connecting line is rotated with respect to the heel line, the expression is quantified as COP rotation in degrees. If the heels were not at the same height, the extension norm for normalized is added to the value. In any case, the COP rotation data are thus always comparable. In the lower left part of the screen you will find the so-called average matrix. That's the interpolated image with the average pressure values that loaded the sensors over the recording duration. Provided that the patient did not move willfully during the measurement, this is a quick and representative insight into the actual pressure distribution. The index matrix displayed to the right of it has the same display options, but it shows the time course of the pressure conditions based on movement and sway. In the first view, you will always see a grayed out image. You can then start the video display via the video control in the blue header bar. The pressure images are color scaled. As the pressure increases, the model is first displayed in light blue, then dark blue, dark green, light green, yellow, orange and red. It is thus easy to see where the foot is exposed to high load peaks. A self-contained red area in the midfoot, for example, is rarely to be expected. This indicates a lowered longitudinal arch. On the other hand, a broadly distributed red area in the forefoot, possibly with several separate pressure zones, indicates a lowering of the anterior transverse arch, so we have a splay foot. A flat foot does not necessarily appear with a pressure peak, but with an evenly distributed pressure pattern and a noticeably widened midfoot. But it becomes more difficult when determining a high arched foot or a rear foot eversion. Both foot types are characterized in a static measurement by missing pressure values in the midfoot. The high arched foot because of the convex upward lifted longitudinal arch, and the rear foot eversion by the eversion and the inward rotation of the longitudinal arch, which also lifts the midfoot off the ground. In some cases, the concrete pressure distribution in the forefoot or the black dot of the respective pressure maximum displayed per foot can help with differentiation, but in many cases, however, the difference only becomes visible in a dynamic measurement. Analogous to the COP calculation of the individual feet, the total center of pressure can also be calculated using the pressure values recorded on both sides. This is then based on the total weight distribution and shows the force distributions displayed in the diagram relatively clearly. Another feature is corner distribution values as a percentage. They distribute the sum of the pressure signals into 4 quadrants, which are divided via the x and y position of the center of pressure. This allows a somewhat more accurate statement about the force distribution. Thus, a unilateral takeover of 50% can consist of 25% forefoot and 25% rear foot, but equally of 40% forefoot and only 10% rear foot. This may allow a completely different conclusion to be drawn about the ascending muscle chains. In a 40-to-10 balance, the tension ratio between dorsiflexors and plantar flexors will be completely different than in a 25-25 balance. Look at pelvic torsion or pelvic rotation when the situation varies from side to side. Or at the pelvic tilt and lordosis angle in the case of a higher forefoot or rear foot loading on both sides. If the coloring display does not allow you to differentiate sufficiently, simply drag the slider under the matrices further to the left. In this way, you reduce the display threshold so that less stressed foot zones are highlighted a little better. However, this also tightens the boundaries between the color gradations. At the lower right edge of the screen there is another display of the weight distribution. It initially consists of 2 levels. Outlined in green are the normative ranges already mentioned above, for the COP position according to anterior-posterior and right-left. The colored area is the actual average position of the center of pressure, as also shown in the above diagrams. Now, when the video is started, a gray area is added indicating the center of pressure distribution over time. The content of the COP stabilometry tab is completely focused on the representation of the variable behavior of center of pressure and body. Once again, the parameter area can be found at the top left. All parameters listed there deal with the total COP resulting from the pressure data of both feet. The first 2 entries show the total range of movement as an amplitude value, so to speak. Thus, the sum of the lateral movement to the left and right results in the complete range within which the COP has moved. The same applies to the anterior and posterior movement. Not to be confused here is the total COP movement. all vertical and horizontal deflections are added up here. In the example, this gives us a total value in millimeters of XYZ anterior, posterior and XYZ lateral. This results in the COP trace. That's the total distance covered by the center of pressure. This is usually somewhat less than the sum of the total COP movement above it. To explain, if the COP moves perfectly diagonally by 10 mm to the front left, this corresponds to a movement of 7 mm to the side and another 7 mm to the front. The values, therefore, result from a related but not identical approach. The COP area indicates the area covered by the COP over the entire measurement period. The speed corresponds to the quotient of total COP trace and the recording duration. It indicates the speed at which the COP variation took place. This information is presented in graphical form in the COP movement section. The curves shown here represent the trajectory of the center of pressures. Light blue for the total COP, royal blue for the COP on the right, and red for the COP on the left. The black dot indicates the COP position at the beginning of the data acquisition. The dashed outline covers the entire range of motion of the COP points. In the light blue trajectory, the value indicated at the top of the outline coincides with the summed lateral motion in the COP parameters. The value on the side corresponds to the sum of anterior and posterior motion. Small differences between graphical and tabular values may result from rounding errors. In addition, a green dashed ellipse is added to each graph. This shows the expected extent of the body sway. Although these graphs clearly show the extent of the fluctuation, they do not provide any information on the variation over time of the fluctuation. This is shown in the graphs on the right of the image. The upper graph shows the lateral movement of the COP in yellow, of the COP left in red, and of the COP right in blue. An upward deflection of a curve corresponds to a movement to the right. A deflection into the negative range indicates a movement to the left. The lower graph shows the COP movement to anterior-posterior, again red for left and blue for right. The AP movement of the total COP is shown here in green. Positive values correspond to an anterior position, negative to a posterior position. So what are these graphs about? On the one hand, it can be recognized here whether certain maximum deviations result from a repeatable fluctuation behavior or only represent one-time outliers. Furthermore, it can be seen here to what extent the overall COP is influenced by the fluctuation in the side COPs. In this case, the three curves would run quite harmoniously. Should the overall COP run in a completely different direction, this would indicate a greater influence of the upper body on the center of pressure. Even if this result tab does not have its own video control, an index bar is offered in these graphs, marking the moment selected in the video control of the first result tab. This view is a slightly larger representation of the matrices of the Results tab summary. There are more visualization options here. Choose whether you want the pressure data to continue to be displayed in interpolated form, or perhaps you would prefer to see it as a representation of the sensors that are actually loaded. You can also view the pressure data of the index matrix in 3D instead of two-dimensionally. This is used to separate pressure areas not only in terms of color, but also spatially. To the right, you can set the data to your preferred standard view. But you can also select an individual view by moving the mouse pointer into the index matrix and keeping the left mouse button pressed. Drag the mouse up or down. The pressure image rotates vertically around the horizontal axis. If you drag the mouse sideways, the image rotates around the vertical axis. And if you hold down the Alt key and drag the mouse sideways, the image rotates around the center axis. So this concludes this tutorial video. I hope you were able to learn a few new things again and see the presented measuring system with new eyes. If you enjoyed this tutorial, we'd love for you to tune in to our other trainings videos as well. So keep at it and see you in the next tutorial video.